So this is a great figure showing the overlap. The rod is shown with this R1, okay, this thin line, and then the cones are shown in L, M, and S, and so those are for long spectrum, medium, or short. So short is the high energy here, right? So that's this violet. Medium would be the green, and at long would stretch, and that would be showing your red or detecting red in your eye. And then here in blue, you see the IPRGCs, and so that's somewhere in between the green and violet, but it's broad, and so the main thing about IPRGCs is that they're not sensitive at all. So if you were ranking them, it would be by far the rods are the most sensitive. So at night, that's what you're using, your rods. Then cones can see, you have 3 different cones that can detect different colors, and that's daylight and you're detecting color. And then the IPRGCs need a lot of light to detect. So when you wake up in the morning, if you have bright light, that will set your circadian clock. What kind of problems can you have here? So the most well-known color blindness is the red-green color blindness. So you see these M&L in the cones, the M&L wavelengths overlap a lot. So if you have a mutation where they overlap even more, that means you can't really start to differentiate the signal coming out of those, and that's red-green color blindness. You can also have color insensitivity. So that's where, imagine you have many more cells that have S cells than L cells. That would be, so this curve shows the likelihood of a photon of that wavelength being absorbed, right? So in these S cones, the most likely wavelength is around violet, right? Now let's say you have 3 times as many S cells as normal. Well, the world is going to look more violet to you because you're detecting more of them, not because it is more violet. In the background here in this gray line, you see what sunlight is. And so it's black body radiation. It's basically very broad. This is, I think, at 10 a.m. in California. And then in this black line here, you're seeing fluorescent light. So fluorescent lights is very short, narrow peaks, and so that's why it's not it doesn't look good in photography, right? So black body radiation is what the sun makes, and that's this wide bell curve of light, and so all the colors look real because every type of light can bounce back. Fluorescent just has these peaks, and so you get very harsh looking light. And this can affect your circadian rhythm. So here's a bunch of different fluorescent lights, and so largely they can look different because, one, you're seeing the wavelength of the fluorescent coming off, but you're also seeing they coat the fluorescent lights in an incandescent paint, and so the fluorescent light hits that, and whatever wavelength the incandescent sends off, you also get that, and that kind of creates a warmer glow. But so you can imagine if you had this peak here around 500 that we're seeing in this fluorescent light, that is going to trigger, if you had a lot of that, that's going to trigger your IPRGCs, which will trigger your circadian rhythm as if it's daylight. So if you're around fluorescent light at night that has a peak there, that's bad. But during the day, you would want fluorescent lights that have that.